What's up, everybody? Today we're going to talk about MPC, not to be confused with MPC, which is a whole another thing, right? And MPC, model predictive control, is a type of optimal control, right? But it has some different flavor compared to the control algorithms that we have been, dealing with. In that it is not, in a way, real-time control algorithm, right? And we are going to talk about what that means, right? Okay, so let's not worry about the control algorithm itself, right? And let us introduce this control algorithm through a really simple, easy example. And okay, this is the motivating example that we are going to look at. Here we can see x dot equals ax plus u, right? This is a really simple state dynamics equation. All right, this is the system that we are going to, and take a look at. And first of all, for MPC, for you to implement MPC, you need to discretize the plant, right? And we mean this, right? Okay, so let's discretize and let us use the simplest discretization algorithm. Okay, forward earlier, right? Okay, all right. And by discretizing, we get this, all right? And all right, let's do some manipulations. Okay, here we have this, and let's isolate x plus 1, right? Okay, we get this, and let's arrange the terms. Okay, so here t is the sampling. I don't even, to be honest with you, I don't even need to talk about that much. T is sampling period, right? And you can take it like 0.1 or 0.001 or something, right? Depending on the, how sluggish or how, fast your system is. Okay, so first of all, the problem itself is linear, right? And maybe I can do this like in two parts. MPC, how to implement MPC for linear systems, right? And by the way, we are focusing on state feedback type MPC. Okay, and maybe hopefully in the part 2 of this topic, we will look at MPC for nonlinear plants. All right, so here this is linear. Okay, and if you look at this is also linear, right? X of x, right? And the coefficient is something that we know, and u of x, again the coefficient is something that we know, and constant numbers. Okay, so here this is k, and maybe this is our x k1, right? X of x, and this is k equals 1, k equals to dot dot dot, and n. Okay, capital N. All right, so, and here maybe I should copy this, copy, paste. Okay, and here this is u, right? Okay, and we need to, this control problem here can be constructed or can be viewed as a optimization problem, basically, right? And in that optimization problem, we need to determine 1, 2, dot dot dot, n numbers. And since this is like, this u is u in r, okay, and this is not the like vector type problem for the motivating example that we are looking at. All right, so we need to solve this optimization problem, and our decision variables are n numbers. We need to find those n numbers, right? Okay, and this is like your first view. This is this probably would be your first view on the problem, MPC problem. But later, if you write down the equations and do some manipulations, and you would come to the conclusion that you need to, on top of finding u of x, right, or u numbers and u input numbers, right, and you need to also find an capital N, I mean x numbers, right? You need to find the, I'm going to draw it like if it is like a continuous sum, but it's not continuous sum, it's discrete sum, right? Okay. And this is your control input, okay, that you need to provide the system to drive the states to origin, all right? And by doing that, your states will have something like this, for example. And of course, this and these signals are discrete time. Okay, I'm just drawing like it is continuous time, all right? And you need to find n u, right, numbers, right, u of k. Basically, I think I should, you need to find u of k, where k is from 1 to n, and on top of that you also need to find x of k, where again k is from 1 to n. All right, so you need to find 2n numbers, right? Okay, what we are optimizing, right? What is the objective function? You can do something like this. You can do something like this. Okay, maybe I should make it something like this. Okay, all right, this can be your objective function, right? Okay, and philosophically you need to find u of k, right, u trajectory. But if you look at the problem deeper, right, and you'd come to the conclusion that, hey, I actually need to find state trajectories as well, right? Because here we can see there is a variation, a strong variation between input and state trajectories. Okay, here if we look at this equation, right, and we would come to that conclusion. All right, so right, and since this is linear, we don't have to do much about this. Okay, and we are going to try to solve this problem and using YOLMIP, right? And as STP solver, you can use STP-T3, or started using MOSEC, right? And okay, MATLAB, YOLMIP, and MOSEC. Okay, these are three things that you need to have, right? Or some type of variations of that. And now look, I'm looking at my screen and I'm thinking about whether to move to MATLAB right now, or if there is something that I need to discuss. And okay, before moving forward, right, and let me move this term, okay, and write down this is objective function. Okay, right. And in this problem we are considering that we know x of 1, right? Here this is x of 1, and we also want to impose this constraint, which is the following: x of n equals 0, right? These two constraints. Okay, and yeah, and maybe you like to impose some type of maybe u minimum, right? Your whole input trajectory, each data point being limited, right? And maybe you have u minimum and u maximum. For example, maybe what you have is some type of voltage source, right? And changing values are the only, I guess, feasible input signals for you to have is 0 and 5 volts, for example, right? And in that, I mean, you using this information, you would impose that type of constraint on your problem, right? And also, we are not imposing any other rate limiter constraints, right? For example, we can also do something like this. Let me write down. U rate limit, right? Because you can solve that problem and your solver will can give you something like this. Okay, right? I mean, of course, just like 0 volt, 5 volt, and minus 5 volt or something, right? And maybe you don't have the capability that you just switch from 0 to 5 in one time step. Maybe you don't have that type of capability, right? Maybe you need to impose some type of rate limiter into your control design, right? And if you can, and this is a number, and these are all these three, u min, u max, and u rt rate limiter, right? They are numbers that you know, right, that you are going to impose on your problem. Okay, and maybe using those type of constraints on top of your construction of your general problem, you will have something like this. Okay, right? And at the end of that, you will have, what you have is something that is sandwiched between your allowable input limits, right, and also the change of your input, right, with respect to the change or your input speed, let's say that, right? Your u dot is also, maybe let's draw like u dot, right? And I'm talking about abstract terms now, and your u dot is in some allowable limits, right? Okay, that you know your problem has. Okay, and now I am looking at the problem, and so and final words, right? Here, what we are going to find is this. We need to determine, right, x of k and u of k, and we can call them as respectively state trajectory and input trajectory. Okay, and also again for k goes from 1 to n. Okay, that's great. So we can just create x vec, right? And this is like the vector, right, having one row and n columns, right? Okay, and same goes for u. I am talking about these things so in the program itself, right, optimization program, and you would have easier time to understand the whole, process. And okay, again, this is a vector and this is a vector, right? All right, now we are going to initiate those vectors as being stp var, which is a notation that's used for in YOLMIP. All right, so let me change the screen. Okay, here, let me just delete all of that, and again here, right, you need to add your MOSEC or SCP-T3 SCP solver library, and also your YOLMIP, right? Okay, all right, and all right, just clean the memory, and this is, I think you are able to see Okay, let me script, but yeah, I should make it bigger. And of course, definitely you are able to see that. Okay, as you can see, it is like 20 lines of code, right? Okay, that's great. This is our state equation, right? Dynamics. And n, capital N, of course you can just do like 10, right? 100, maybe 1000, totally depends on your problem. And t, again the sampling period, right? Again, this, I mean, these are just you will choose those variables just by basically trial and error process. Okay, again, this is something that we have talked about, right? And UVEC, basically input trajectory that you need to supply to your system to get your expected, I guess, state trajectory, where at the end of that trajectory your states converge to the origin or your reference point. And but this is a regularization problem, so we want our state to, I'm not saying states because this one-dimensional problem, and in the future we will talk more about this MPC, other type of MPC problems. We will, look at that more. All right, and okay, and now we are going to, by the way, we just defined our input trajectory and state trajectory as vectors, SCP, right? Okay, we are just telling YOLMIP, hey, we are going to find those variables, and or we are going to use those variables, and these are our decision variables, right? Okay, and all right, what are our constraints? If we are going to put all of our constraints on this object, okay, and since we discretize that, right, we are just going to iterate through our, I guess, time steps, and we will use our main constraint. What is our main constraint? Which is the dynamics that we have, right? And of course, this is in continuous time domain, and we just discretize that, right? Okay. And I'm looking at my screen. Okay, everything is in order. And okay, if you look at this and maybe keep that in mind, and let's go back to the tablet, right? Okay, that term that I just highlighted is the same as this. Okay, all right, so we are just imposing this constraint. What is that constraint? Which is the dynamics of our plant. All right, let's go back to MATLAB again. Okay, I just commented out this. I will solve the original problem, and then we will look at the results, and then we will impose more like harsh constraints on our problem, right? And then we will look at the solutions. Okay, all right, this is the dynamics basically. Okay, all right, we are just imposing that. Okay, that's great. And on top of that, here, this is our, we just, I mean, for the problem's sake, right? And we just pick that value 10. We want our state, I mean, 10 is our initial condition basically. Okay, all right. And we also want to impose that constraint, right? This is a hard constraint that we want our states to converge to 0, and we totally want our state to be, I mean, 0 at the end of this like n time step. Okay, all right. And also and optimization problems are like, I mean, any other thing with that you have with the computers, that you need to be very careful about what you wish for, I guess, or what you want the computer to do, right? Because computers are really good at what they're doing, but you need to be very good at, I mean, explaining your or conveying your problem to the computer or optimization program solver, right? So, and if we, for example, this is some type of input constraint, right? And if we don't employ that constraint, I mean, computer will just, I mean, employ or find tremendous amount of input signal, right, with large magnitude, right? And this is, of course, this is not something that you would usually have. I mean, for any kind of problem, you would have constraints, input constraints, state constraints, rate limit constraints, right? X dot, U dot, etc. type of constraints, right? And maybe you double dot constraints, right? Maybe you are okay with the U dots. Maybe you just found and you just computed your U trajectory, and then you look at U dot signal, U dot trajectory, like input, the change of input trajectory, and it is okay. But maybe you double that. Maybe, you know, acceleration of your input signal trajectory is not suitable for your application, right? So, and usually you wouldn't impose that type of constraints directly. I mean, directly, you wouldn't use that type of, you are not in a position to employ that type of constraints, right? For example, if you are using linear controllers like LQR, you know, H infinity control, you know, dynamic output feedback control type of, you know, controllers types. I mean, you would impose that type of constraints by through indirect means, right? But what MPC or why MPC is special is, I can say, MPC allows you to, you know, impose that type of really strict and specific constraints directly. Okay. All right. So just this is our constraint, right? Okay. And we also want to, you know, start from 0 for our input signal. Input, yeah, trajectory basically. All right. And we are just defining our SCP solver, right? And this is our, again, if you look at the, you know, tablet in a couple of minutes ago, and we basically minimize the state trajectory to impose our idea, or to convey our idea that we want state trajectories to converge to 0 as fast as possible, right? Okay. All right. And diagnose, we just, you know, get the results, right? Okay. So let's run this. Okay, it's gonna take some time. Okay, it says successful solved, right? Problem equals 0. That's great. That's great. And let's plot them, right? Here we can see, right? Let me just zoom it a little bit, right? So this is our state. Again, it starts from 10, right? And it also converges and also goes to 0, right? Okay. And if we look at our input signal, it again starts from 0, k equals 1, u equals 0, right? And as soon as the, you know, whole process starts, u goes to minus 20, which is like its lower limit, right? And then goes to 0, right? And it is some type of switching controller, right? It just, you know, switches between those two values. And so it's all right, it is working, right? But maybe you are not happy with that type of change. Maybe you don't have the capability that your input or actuator can apply or go between like -2 to 0 in 1 or 2, you know, time steps, right? What would you do? How would you impose that type of constraint? You would impose this. Let me just Control T, right? Okay, maybe you don't have, yeah, you know, you just impose this constraint, which is to say, I can only move or change one unit between the time steps, right? Whatever our actuator is. Okay, so let's run it, right? Let's see if it is able to solve. All right, successful solved, it says, right? And let's again plot the results, and here we go. We have state and input trajectories, right? And if you look at this, if you look at the state trajectory, this is like, yeah, I mean, this is something that we would like to see, right? And also for input, this is something that probably our controller, or this is something that we would our control to produce, right? Okay, and I'm looking at this, and all right, everything is in order, I guess. Okay, so I guess this should be it, right? And yeah, this, let's call it part 1 MPC. Okay, all right, that's it folks, and thanks for watching.